Picture a ring of galaxies so wide, light takes over 1 billion years to cross it. That is real, and it should not exist. A telescope built to look back at the start of time just found it hiding in the dark near a group of stars called Boötes. Tonight we go there. We visit a ring that breaks a rule scientists thought was solid. We visit a web of 164,000 galaxies, mapped in more detail than ever before. And we visit the black holes hiding inside it, shooting jets at half the speed of light. If your brain likes being stretched, hit like and subscribe before we start. Get comfortable. We begin now. A telescope built to see the birth of the universe just found something it was never supposed to find. It was quietly scanning a patch of sky near a group of stars called Boötes, mapping galaxies the way a kid maps stars taped to a bedroom ceiling. Then a clear pattern showed up, sharp and unmistakable. A ring made of galaxies, so wide that light needs over 1 billion years just to cross from one side to the other. Picture the drive from New York to Los Angeles. Now picture that distance stretched out until it disappears completely inside something else. Something so much bigger the entire width of the country would not even register as a dot on it. That is the scale we are talking about. And it is sitting quietly in the dark, waiting for anyone with a strong enough telescope to notice. Scientists have a rule about the universe. Zoom out far enough, and everything should look roughly the same everywhere, like chocolate chips spread evenly through cookie dough. No giant clumps hiding in one corner, no giant empty gaps stretching across another. Just even spread, all over. Once the scale gets big enough, this ring breaks that rule in the loudest way possible. It forms a shape instead, a clean, obvious, unmistakable shape, and a shape that big is not supposed to hold together, let alone exist at all. Here is the part that turns curiosity into chills. Nobody planned this discovery. It came from a graduate student combing through data, hunting for something else entirely, and instead finding a pattern too clean to be an accident. That part is confirmed. The ring is real. It has been measured, checked, and measured again by different teams using different methods. What made it, though? That part is still a mystery. Nobody has a settled answer. Not yet. Some structures in space get explained fast. A star burns out on a predictable schedule. A comet follows a path scientists can chart years in advance. This is different. This is a shape sitting in the deep past of the universe, at a distance where the light left it long before Earth even existed. Whatever formed this ring did its work when the universe itself was still young. That timing alone should make it impossible. Young universes do not have enough time to build anything this size. Think about a puzzle piece that is too big for the box it came in, no matter how you turn it. That is the situation scientists are facing right now. Every model of the universe assumes structures grow slowly, small pieces joining bigger pieces over billions of patient years. This ring seems to have skipped steps nobody thought could be skipped, growing faster and bigger than the rulebook allows. The person who found it did not stumble onto a one-time fluke, either. She had done this before. A few years earlier, she found another giant structure in the exact same region of sky, an arc-shaped pattern that made astronomers raise their eyebrows the first time around. Two impossible shapes, both hiding in the same patch of space, both waiting years to be noticed. So, tonight, we are looking at the start of a much bigger problem. One sitting quietly in the data, waiting for someone patient enough to notice it. And the deeper we go, the stranger this gets. Space feels empty when you look up at night. Dark, quiet, scattered with a few points of light, maybe a plane blinking past. That picture is wrong, or at least badly incomplete. Zoom out far enough, past stars, past galaxies, past entire galaxy clusters, and a hidden structure appears. Scientists call it the cosmic web. It looks less like scattered dots and more like a spider's web stretched across billions of light years, with galaxies clumped along invisible threads and huge empty gaps sitting in between them. Here is a comparison that actually sticks. Picture bathwater draining out of a tub, with soap bubbles clustering along thin lines of foam and big patches of clear water sitting empty in between. The universe arranges itself the same way, just on a scale that breaks the human brain completely. Galaxies are not scattered randomly like sand thrown across a table. They collect along filaments, thin bridges of matter connecting to bigger hubs where even more galaxies pile up together. Between those filaments sit voids, spaces so empty they stretch for hundreds of millions of light years, with almost nothing inside them at all. For decades, scientists could only guess at the full shape of this web. Older telescopes caught blurry pieces of it, faint smudges, hinting at structure without ever proving it clearly. It was like trying to understand a spider's web by squinting through a foggy window from across the street. You could tell something was there. You could not trace its exact shape, and you definitely could not map how it changed over time. Then a new telescope changed the picture completely. It is called the James Webb Space Telescope, and it sees light that older telescopes could barely detect at all. Light that has been stretched and dimmed after traveling for over 10 billion years across empty space. That kind of light comes from galaxies so old and so far away. They formed when the universe was still in its toddler years. Seeing that light clearly is like finally taking off a pair of fogged-up glasses you did not even know you were wearing. With that clearer vision, scientists built the most detailed map of the cosmic web ever made, confirmed, not guessed, and published for anyone to check. A survey covering a patch of sky about the size of 3 full moons side by side, packed with over 160,000 galaxies. That map did something no earlier map could manage. It showed exactly where galaxies grow fast, where they slow down, and where they stop forming new stars completely. This is where the ring from earlier fits into a much bigger picture. The cosmic web is supposed to follow patterns scientists can predict with math, clumps here, gaps there, growth following a known and steady timeline. A ring that big, sitting in a spot the models never predicted, is like finding a tangled knot in a web that should not be tied at all. Something at the edge of the pattern is asking a much bigger question. If the web mostly behaves the way scientists expect, what is different about this one place that lets something so strange take shape? That question does not have a full answer yet. Every big discovery starts somewhere small, and this one started with a graduate student sitting alone in front of a screen full of numbers late at night. She was mapping quasars, the blazing cores of distant galaxies, using them like streetlights to trace the invisible structure of space around them. Slow, careful, unglamorous work. The kind of work that rarely makes headlines or gets a second glance from anyone outside the field. Then a shape appeared that did not belong there. Quasar after quasar lined up, curving into an arc instead of scattering randomly the way the standard models predicted they should. She checked it again. She checked it a third time, running the numbers a different way each time. The arc held steady. It was confirmed, not a fluke buried in noisy data, not a trick of a tired eye staring too long at a screen. A structure nearly 3 billion light-years long, curling across the sky like a smile drawn by something enormous and unseen. That first discovery, called the Giant Arc, should have been strange enough on its own to end the story there. But then, working through more data from that same slice of sky, the same student found a second shape. This one closed into a full circle, a ring, sitting almost exactly where the arc had already been found, in the same general region near the constellation Botas. Picture flipping through years of old family photos and noticing the same stranger standing quietly in the background of 2 different pictures, taken miles apart on different days. That is the kind of coincidence scientists were suddenly staring at. 2 giant, rule-breaking structures found by the same person sitting in nearly the same patch of the sky, only years apart. Here is where the trust signal matters most. The ring's existence is confirmed through multiple independent checks of the data, run by more than one research group. What is still open, still debated, is why it exists at all, and why this particular slice of sky keeps producing structures that should not be possible according to the rules everyone learned in school. Scientists do not throw around the word impossible lightly. When the data forces that word into a headline, it usually means something in the current picture of the universe is incomplete. Discoveries like this rarely arrive with fireworks or a press conference. They arrive quietly, buried inside spreadsheets and graphs, waiting for someone patient enough to notice the pattern hiding underneath. This time, someone did. And once she noticed, the rest of the astronomy world had to sit up and pay attention, because a shape like this does not stay peaceful for long. It challenges one of the oldest assumptions in the entire field. Imagine spending months staring at rows of numbers, the kind of task that could easily blur into background noise. Then one pattern refuses to blur. It sharpens instead, getting clearer the closer you look, until ignoring it stops being an option. That is the moment real discoveries happen, not in a lab explosion or a dramatic announcement, but in a quiet room where someone refuses to look away from something strange. The scientific community did not accept the ring overnight, either. Papers got written, other researchers pulled the same data and ran their own independent checks, trying to find a mistake, a flaw, anything that might explain the shape away. None of them could. The ring held up under every test thrown at it, which is exactly how real discoveries earn their place in textbooks instead of getting quietly forgotten. Two structures, one tiny corner of space. And the deeper scientists dig, the less this looks like an accident of chance. Every science has a rule book, and cosmology's most important rule is simple to say and surprisingly hard to shake once you understand it. Zoom out far enough, and the universe should look the same in every direction. No favorite side, no giant clumps hiding in one corner, while another corner sits nearly empty. Just smooth, even, almost boring sameness once you zoom out enough. Scientists call this the cosmological principle, and nearly every model of the universe leans on it like a foundation holding up the walls of a house. Think about shaking a bag of sand and pouring it slowly onto a flat table. Up close, you would see individual grains clumped into random little piles, some taller, some barely there. Zoom out, though, and those piles blend together into a flat, even layer stretching across the whole table. That is exactly what the universe is supposed to do at the largest possible scales. Individual galaxies can clump into small groups near each other. Zoom out far enough, though, and those clumps should disappear into a smooth, even spread with nothing standing out. The big ring breaks that picture in a way that is hard to explain away. A ring 1.33 billion light-years across is not a small clump that quietly disappears once you zoom out. It is large enough that it should show up as an obvious bump in the smoothness, a spot where the universe refuses to behave like every other spot around it. Scientists have calculated limits on how big a structure is allowed to get before it breaks the rule of sameness completely. This ring blows straight past that limit. Here is why that matters beyond one strange shape sitting in the sky. The cosmological principle sits at the heart of modern cosmology. It is baked directly into nearly every calculation cosmologists use, from figuring out the age of the universe to predicting exactly how galaxies form and grow over time. If the universe has spots that are not smooth, and even at scales this enormous, then some of that underlying math needs a serious second look. That does not mean everything scientists currently know about the universe collapses overnight into chaos. It means a crack has appeared in a wall that used to look completely solid and unshakable. Cracks like this have shown up before in the long history of science, and they usually lead somewhere important, either a careful fix to the existing model or an entirely new discovery that reshapes it. The honest answer right now is that nobody knows which outcome this leads to. The ring is confirmed. The size is confirmed. The fact that it breaks the expected smoothness is confirmed. What comes after that is still open territory, a genuine unsolved question sitting right at the edge of modern cosmology, waiting for someone to solve it. Think about how strange it feels when a rule you trusted your whole life suddenly has an exception. Maybe a teacher told you a math rule always works, until one problem breaks it completely. That small moment of doubt, multiplied by 1 billion, is roughly what cosmologists are feeling right now. The rule was supposed to be airtight. One ring in the sky just proved it might not be. Scientists are not panicking over this, and that matters too. Science survives by finding exceptions and figuring out what they mean, not by pretending they do not exist. The Big Ring is exactly the kind of exception that keeps an entire field moving forward, forcing smarter questions and better tools. Right now, it sits there quietly, daring anyone to explain it properly. Size alone does not make the Big Ring frightening. Timing does. This ring sits roughly 9,200,000,000 light-years away, meaning the light-reaching telescopes today left that spot when the universe was still young, only a few billion years old. That is the equivalent of looking at a photograph of a toddler on their first birthday and somehow seeing a fully built city standing in the background, a city that should not have had time to exist yet. Structures in the universe are supposed to grow the way a snowball grows, rolling downhill, slowly picking up more material bit by bit as it goes. Small clumps of matter pull in more matter through gravity, forming bigger clumps, which pull in even more over unimaginable stretches of patient time. Billions of years typically stand between a small seed of matter and a truly giant cosmic structure. That is the timeline scientists rely on to explain how galaxies, clusters, and even bigger structures slowly come together. The Big Ring does not fit that timeline at all. At the point in cosmic history where we see it, there simply should not have been enough time for gravity to pull together something this massive, this organized, and this enormous. Picture trying to build a life-sized replica of an entire football stadium, using only the time it takes most kids to build a sandcastle at the beach. The materials might technically be there. The time definitely is not. This is where scientists split into different camps, each one chasing a different piece of the puzzle. Some suspect the models used to predict growth speeds are simply missing something, some ingredient that lets structures form faster than expected under very specific conditions nobody has pinned down yet. Others wonder if something entirely new is at play, a process nobody has fully identified or measured before. Both ideas remain theories. Neither one is confirmed as fact. What is confirmed is the age problem itself, sitting right there in the numbers. Distance in space also means distance in time, since light takes real time to travel across the emptiness. The ring's distance places it firmly in the early universe, a stage when galaxies were still young and structures were still supposed to be small and scattered. Finding something this vast at that early stage is like finding a fully grown oak tree standing tall in a forest that was only planted last spring. That kind of impossible timing does not resolve itself quietly on its own. It forces a choice. Either something is wrong with how scientists calculate growth speeds during the early universe, or the ring formed through a completely different process nobody has pinned down yet. Both options carry big consequences for how the entire story of the universe gets told from here on out. Picture a school project due in 1 week, but the assignment actually needs 6 months of work to finish properly. That mismatch, a task needing far more time than it was given, is the exact problem cosmologists are staring at with this ring. The universe handed itself an assignment and somehow turned it in early, finished, with no visible shortcuts anyone can point to. Some researchers have gently suggested that maybe gravity itself behaved slightly differently in the deep past, working a little faster or a little stronger under conditions that no longer exist today. That idea remains a theory, nothing more, floated as one possible explanation among several. Still, the fact that serious scientists are willing to question something as fundamental as gravity's behavior shows exactly how seriously this timing problem is being taken. Whenever a discovery looks this strange, scientists check for the most boring explanation first, before letting themselves get excited. Boring explanations are usually right, so before anyone celebrated a ring-shaped structure breaking the rules of cosmology, astronomers had to ask a basic, unglamorous question. Is this ring even real, or is it just a trick played by gravity itself? Here is the trick in question. Massive objects in space bend light as it travels past them, the same way a curved piece of glass bends whatever image sits behind it. Scientists call this gravitational lensing. A distant object can appear stretched, smeared, or even duplicated if its light happens to pass near something heavy enough on its long journey to Earth. If a foreground galaxy cluster happened to sit in exactly the right spot, it could theoretically bend and stretch the light from background galaxies into a shape that only looks like a ring without any real ring ever existing at all. Picture looking through the thick bottom of a glass bottle at a row of streetlights across the road. The lights would blur and curve into shapes that do not match what is actually sitting out there in reality. That is precisely the kind of illusion scientists needed to rule out before they could trust their own exciting data. So they checked, carefully and repeatedly. Multiple checks from multiple angles using the redshift of each individual galaxy inside the ring, which works essentially like a distance and timestamp based on how the light has stretched during its long journey. If the ring were only a lensing illusion, the galaxies inside it would show random, scattered distances, since lensing does not care at all about a galaxy's true depth in space. Instead, the galaxies lined up at strikingly similar distances, consistent with an actual physical structure sitting together in space, rather than a bent reflection of something else entirely. That result mattered enormously to the whole discovery. It meant the ring was not a mirage created by gravity playing tricks with distant light. It was measured as a real, physical arrangement of galaxies, sitting together in space, forming an actual shape rather than an illusion pretending to be one. This is exactly the kind of trust signal that separates real, careful astronomy from wild speculation online. The lensing explanation was tested thoroughly, and it did not hold up under pressure. That leaves the harder, stranger question sitting untouched and waiting. If it is not an illusion, and it is not simple coincidence, something genuinely shaped this ring into existence. It is worth pausing on how much work went into ruling out just one possibility. Measuring the redshift of a single galaxy takes careful analysis. Measuring dozens of them across a structure over 1 billion light-years wide takes teams of researchers working through mountains of data, point by point. That is not a quick guess made from a blurry photo. That is a slow, careful process built specifically to catch mistakes before they turn into headlines. With the easy explanation eliminated, scientists had to turn towards stranger ideas, the kind that used to live only in theoretical physics papers nobody outside the field ever read. Numbers alone do not stick in the brain for long. Comparisons do. So here is what a structure 1 1/3 billion light-years wide actually means, laid out next to things that already sound enormous on their own. The Milky Way, the galaxy containing our entire solar system, stretches about 100,000 light-years across. That already sounds massive enough to end the conversation. The Big Ring is roughly 13,000 times wider than our entire galaxy. Picture the distance across the continental United States, coast to coast, and then imagine a structure that makes that distance look like the length of a single football field by comparison. That is the kind of size jump happening here. A jump so large it stops feeling like a bigger version of something familiar and starts feeling like an entirely different category of object. Even galaxy clusters, which are already the biggest gravity-bound structures scientists normally expect to find anywhere in the universe, fall short next to this. A typical large galaxy cluster might stretch a few million light-years across, which already sounds impressive on a normal day. The Big Ring dwarfs that by a factor of hundreds, landing in a different category of object entirely, sitting in a size range that most models never predicted anything could reach in the first place. Before the Big Ring, scientists already knew about other oversized structures, like the Sloan Great Wall, a sprawling arrangement of galaxies discovered years earlier that also stretched far beyond expected limits at the time. Structures like that forced scientists to slowly raise their estimate of how big something in the universe is allowed to get before breaking the rules. The Big Ring did not raise that estimate gently. It smashed straight through it in one discovery. Here is a comparison that hits closer to home than most. Light from the sun takes about 8 minutes to reach Earth on an ordinary day. Light from the edge of our own galaxy takes tens of thousands of years to arrive. Light needs over 1 billion years just to cross from one side of the Big Ring to the other side. An entire civilization could rise from nothing, build cities, invent language, and vanish completely, many times over, in the time it takes light to travel from one edge of this structure to the other. That scale matters for more than bragging rights over the biggest structure ever found in the sky. It matters because size like this pushes directly against the limit cosmologists use to define how large something is allowed to be before it breaks the rule of a smooth, even universe. The Big Ring does not bend that limit gently, it shatters it completely, leaving scientists to explain the pieces. Numbers like these are hard to hold in your head for very long without them slipping away. Once they sink in properly, one question becomes impossible to ignore. What kind of process could organize matter across a gap that enormous and still make it hold together in a shape this clean and unmistakable? Boötes should be an ordinary patch of sky, nothing special. It is a constellation, a pattern of stars used mostly for navigation and old star charts. Nothing that historically stood out as unusual or important. Yet this same region keeps producing structures that break the rules scientists rely on to describe the entire universe. First came the giant arc, an enormous curved formation of galaxies stretched across roughly 3 billion light-years of space. Then came the Big Ring, a closed loop sitting nearly in the same location, discovered by the same person only a few years later. Two separate, confirmed, rule-breaking structures, both hiding in nearly the same slice of sky, waiting patiently to be noticed. Picture searching two houses on opposite ends of a street and finding the exact same rare item hidden in both basements, wrapped the same way. A single strange find might be dismissed as a coincidence. Two strange finds in the same neighborhood start looking like a pattern with a real cause hiding behind it. Scientists have floated one especially bold explanation for why these two structures sit so close together in the sky. What if the arc and the ring are actually two visible pieces of the same larger, unknown structure? Picture a much bigger shape, so vast that human instruments have only mapped small fragments of it so far, with the arc and the ring representing different visible sections of one connected whole hiding just out of view. This idea remains firmly in the theory category. Nobody has confirmed a direct link between them yet, but the idea is being taken seriously, precisely because coincidence starts feeling like a weak explanation the longer this pattern keeps repeating itself. There is another possibility worth sitting with for a moment. Maybe Boötes is not special at all. Maybe similar giant structures exist scattered throughout deep space everywhere, and scientists have simply not surveyed enough of the sky yet to find them elsewhere. Under this theory, Boötes only looks unique because it happens to be one of the first regions studied closely enough, with strong enough tools, to catch structures this size in the act. Either explanation carries big implications for how scientists think about the universe going forward. If Boötes really is uniquely strange, something specific happened there that scientists do not yet understand or have a name for. If similar structures are hiding everywhere across the sky, then the universe may be far less smooth and even than the standard model assumes, and cosmologists have a much bigger problem on their hands than just one unusual ring floating in the dark. Right now, that question remains genuinely open, an honest, unknown, rather than a settled answer scientists can point to with confidence. But the search for more structures like this one is already underway across the sky, and what scientists find next could tip the balance firmly toward one explanation or the other. Think about how a single unusual grade on a report card might just be a bad day. Two unusual grades in a row start to look like a pattern a teacher needs to investigate. Astronomers are running the same kind of investigation right now, pointing telescopes at Boötes again and again, checking every corner of that patch of sky for a third impossible shape hiding just out of sight. Because if two impossible structures can hide comfortably in the same neighborhood without anyone noticing for years, the next question becomes impossible to avoid. What else might be hiding out there that nobody has found yet? When ordinary explanations run out completely, scientists reach for the ideas sitting at the very edge of known physics. For the Big Ring, one of those ideas involves something called a cosmic string, and it sounds like it was pulled straight out of a science fiction script written for the big screen. Cosmic strings are a theoretical kind of defect, a thin, incredibly dense thread that some physicists believe could have formed in the first fractions of a second after the universe began, before anything else existed. Picture the universe as a sheet of ice slowly forming over a lake in winter. As ice freezes, it does not form perfectly smoothly across the whole surface. Cracks and seams appear where different sections meet and push against each other. Cosmic strings are proposed to be something similar, a kind of seam left behind from the earliest, most chaotic moment of cosmic history. Still sitting there, billions of years later, these strings, if they exist at all, would be almost impossibly thin, thinner than a single atom, yet carry an enormous amount of mass packed into that tiny width. That mass would be dense enough to bend space and gravity around it, potentially tugging galaxies into unusual formations as the universe expanded outward, possibly even organizing matter into a ring-shaped pattern over billions of patient years. Here is the important trust signal, stated plainly. Cosmic strings remain a theory. Nobody has directly detected one anywhere in the universe. They exist right now as a mathematical possibility, something predicted by certain versions of physics that describe the earliest moments of the universe, but never yet confirmed through direct observation or measurement. The Big Ring has become one of the pieces of evidence scientists are examining closely to see if it might indirectly support the existence of cosmic strings, without proving it outright or settling the debate. If cosmic strings turn out to be real, the consequences reach far beyond just explaining one ring floating in deep space. It would mean the earliest moments of the universe left behind physical fossils, scars from creation itself, still influencing the shape of space billions of years later, still visible if you know exactly where to look. It would also open the door to entirely new physics, connecting the largest structures ever observed to the smallest, most extreme instant in all of cosmic history. That is a lot resting on one thin, hypothetical thread stretched across the cosmos, which is exactly why scientists are being careful not to jump to conclusions too quickly. The ring is real. The idea that a cosmic string shaped it remains a serious theory, taken seriously by respected researchers around the world, but still unconfirmed, still waiting for stronger evidence one way or the other. Some ideas sound too strange to be real, right up until the evidence finally proves otherwise, and everyone has to update what they believed. History is full of examples like that. Ideas mocked for decades before turning out to be exactly correct, once the right instrument finally caught up to the theory. For now, the cosmic string idea sits exactly on that edge, somewhere between wild speculation and a genuine breakthrough waiting patiently to happen. It is easy to hear the phrase "rewrite physics" tossed around and let it slide past without really landing in your brain. So, here is what that phrase actually means. If cosmic strings, or something like them, turn out to genuinely explain the Big Ring, physics right now runs on a small set of trusted rules, tested over and over across decades, used to predict everything from how planets orbit their stars to how entire galaxies form over billions of years. Confirming something like a cosmic string would not throw out those existing rules completely. It would mean adding an entirely new chapter to the rulebook, one describing a type of object that current physics only allows as a theoretical possibility right now, not yet a proven reality anyone has measured directly. Picture a map of the world missing an entire continent, with only rough sketches filling in the blank space. Explorers might have theories about what could be out there, guesses based on scattered clues and secondhand stories. Confirming a cosmic string would be like finally landing a ship on that missing continent and proving the old sketches were pointing at something real all along, hiding just past the edge of the known map. Here is why this matters beyond simple academic curiosity locked away in a university office. If cosmic strings are real, They would connect two extremes that currently feel completely disconnected in physics: the unimaginably tiny scale of the universe's first fraction of a second, and the unimaginably massive scale of structures like the Big Ring, 1.33 billion light-years wide. Right now, those two extremes get studied using almost entirely different tools and different branches of science that rarely talk to each other. A confirmed link between them would be a genuine breakthrough, the kind that reshapes entire fields of research overnight. There is a human stake buried inside all of this too, one that reaches beyond textbooks. Every model used to estimate the age, size, and future of the universe leans on assumptions about how smoothly matter is spread out at the largest scales imaginable. If structures like cosmic strings turn out to be real contributors to how the universe is shaped, some of those estimates may need to be recalculated, not thrown away entirely, recalculated, refined, and made more accurate than before. None of this is settled yet, and that needs to stay crystal clear through all of it. Cosmic strings remain unconfirmed. The Big Ring remains unexplained in full. What is confirmed is that scientists are taking the possibility seriously enough to design brand new ways of searching for evidence, rather than dismissing the idea outright and moving on. Real breakthroughs rarely arrive all at once, wrapped up neatly with a bow. They arrive in pieces, one confirmed measurement at a time, one ruled-out theory at a time, slowly narrowing the possibilities until only the strongest explanation survives the process. The Big Ring is still early in that process, sitting closer to the beginning of the story than the end of it. Waiting quietly behind the cosmic string theory is an even stranger idea, one that reaches past the rules of physics inside our own universe entirely. It questions whether our universe is the only one involved in this story at all. Some theories stay comfortably inside the walls of known physics. This next one steps outside them entirely, into territory that sounds more like philosophy than science, except it comes from serious researchers working with real, published mathematics. The idea is called a bubble universe collision. Picture our entire universe as one bubble floating in a much larger, mostly empty space, alongside countless other bubble universes, each one its own separate pocket of space and time, drifting independently. Under certain versions of cosmological theory, these bubbles can occasionally brush against each other or even collide directly, leaving behind a mark in the bubble that survives long after the impact fades. That mark, according to this theory, would not look like a crater or a violent explosion. It would look like a subtle ripple in the structure of space itself, a spot where matter clumped together differently than it does everywhere else nearby, because that region felt the influence of another universe pressing against ours from outside. Picture two soap bubbles floating close together in the air, briefly touching, leaving behind a faint, flattened patch where they met before slowly drifting apart again. Some researchers have floated the idea that a structure like the Big Ring could be exactly this kind of mark, a bruise left behind from a brush with another universe entirely, sitting quietly in our sky for billions of years, waiting patiently for our telescopes to finally grow sharp enough to notice it hiding there. Here is the trust signal, spoken as clearly and honestly as possible. This remains firmly in the theory category, sitting closer to the edge of speculation than even the cosmic string idea from before. Multiple universes have never been directly observed by anyone. Bubble collisions have never been confirmed through evidence. This idea exists because certain mathematical models of cosmic inflation technically allow for the possibility, not because anyone has actually found solid proof that it happened. Still, the fact that serious scientists are willing to float this idea says something important about how genuinely strange the Big Ring truly is. Researchers do not reach for a theory this bold unless the more ordinary explanations keep falling apart under pressure. Every simpler idea, illusions created by gravity, normal growth stretched out over time, has already run into serious problems trying to explain what the data plainly shows. None of this proves other universes exist out there somewhere. It proves that the search for an explanation has widened far beyond where anyone originally expected it to go, starting from one strange ring found completely by accident, all the way out to a theory involving other universes entirely. Step back for a second and notice how far this has traveled. A graduate student sifting through quasar data, a shape that should not exist, a rule about smoothness getting broken, illusions ruled out one by one, theories stretching from ancient cosmic threads to entire other universes brushing against our own. That is the kind of chain reaction one honest question can trigger when nobody is willing to look away from it. And that pocket of sky near Botes is still only one small piece of a much bigger puzzle, because the same telescope responsible for sharpening our view of that ring has also been busy mapping something even larger, a structure that stretches across the entire observable universe. A single ring, no matter how strange, is still one object floating in a big, dark sky. Scientists needed to know if it was truly alone or if it was just one visible thread poking out of something far larger hiding underneath. So they built a telescope program capable of asking that exact question, aimed at mapping structure across a huge stretch of the observable universe. The James Webb Space Telescope has spent recent years staring deep into a single patch of sky, over and over, building up a survey so detailed it earned its own name. Astronomers call it Cosmos Webb, and it stands as the largest survey this telescope has ever run. Picture pointing a camera at the exact same spot in the night sky for over 250 hours total, capturing every faint flicker of ancient light hiding in that patch, one careful exposure at a time. That patch of sky was not small either. Picture holding up 3 full moons side by side against the sky, and that gives you a sense of the area covered. Inside that area, researchers catalogued over 160,000 individual galaxies, each one a data point helping to build a bigger picture of how matter arranges itself across billions of years of cosmic history. Here is why this matters beyond just counting galaxies for fun. Earlier surveys, done with older telescopes, could only see the brightest, closest galaxies clearly. Fainter, more distant galaxies stayed blurry or invisible completely, like trying to read street signs from far away at night with weak headlights. The James Webb Space Telescope changed that completely, catching light too faint and too old for anything that came before it. With that upgrade, scientists finally built something remarkable, a detailed 3-dimensional map showing exactly how galaxies cluster together and how they spread apart into empty voids across enormous stretches of cosmic time. Not just where galaxies sit today, where they sat billions of years ago, and how that arrangement slowly changed as the universe aged. This is the moment the big ring stops looking like an isolated oddity and starts looking like a visible piece of something much bigger. The cosmic web itself, the vast skeleton connecting galaxies across unimaginable distances, was finally coming into full focus. And what scientists found inside that skeleton turned out to be just as strange as the ring that started this whole journey. Building a survey this large took years of planning and careful scheduling, since observing time on a telescope this advanced is one of the most requested, most limited resources in modern science. Researchers from institutions around the world contributed to the effort, pooling expertise from different specialties to make sure the final catalogue held up under scrutiny. Because mapping the shape of the universe is one thing. Understanding why it grew that way is an entirely different challenge, one that pulls in mysteries stranger than anyone expected walking into this project. Picture a puzzle with over 160,000 individual pieces, except every single piece is an entire galaxy, and the completed picture shows the actual shape of the universe across billions of years. That is essentially what a team of astronomers built, using data from the most detailed survey the James Webb Space Telescope has ever conducted. Assembling a map like that required more than just pointing a telescope and hoping for the best. Each galaxy needed its distance measured carefully, using a method based on how light stretches as it crosses the expanding universe. Stretched light means older, more distant light. That stretching acts like a built-in timestamp, telling scientists where a galaxy sits and roughly when, in cosmic history, its light first began the long journey toward Earth. Multiply that single measurement by 164,000, and you get something extraordinary. Not a flat, two-dimensional picture of the sky. A layered, three-dimensional map stretching back toward the very edge of observable time, showing galaxies from the recent universe sitting closer to us and galaxies from the ancient universe sitting farther away, layered like the rings inside a tree trunk telling the story of its age. Here is the comparison that makes this click. Picture slicing an onion in half and looking at the rings inside, each layer representing a different point in time as the onion grew. This cosmic map works the same way, except instead of a few dozen rings, it holds 164,000 individual data points, each one a galaxy captured at its own moment in cosmic history. What that map revealed surprised even the researchers who built it. Instead of a smooth, evenly spread universe, the map showed dense clusters of galaxies clumped tightly together in some regions, sitting right next to enormous stretches of nearly empty space in others. That pattern is not random. It follows the shape of the cosmic web itself, the vast structure of filaments and voids that has been theorized for decades, but never mapped in this much detail before. This level of detail is confirmed, published, and available for other scientists to check for themselves. The catalog itself sits publicly online, letting researchers around the world dig through the data and search for patterns nobody has spotted yet. That kind of openness matters, because it means whatever gets discovered next will not rest on the word of just one team. Compare that openness to how earlier surveys worked, often kept closer to the researchers who built them, harder for outside teams to access, and double-check quickly. Publishing this catalog openly invites exactly the kind of scrutiny that strengthens a discovery instead of weakening it, turning one team's careful work into a resource the entire field can build on together. With a map, this detailed finally in hand, scientists could finally ask a bigger question. What forces shaped these galaxies into this exact pattern over billions of years of cosmic history? Somewhere in that mountain of new data, scientists noticed something that did not sit right. Certain galaxies, sitting incredibly far away and therefore incredibly early in cosmic history, looked far too developed for their age. Picture meeting someone who tells you they are only 10 years old, except they are already running a business, driving a car, and living completely on their own. That mismatch between age and development is exactly the kind of problem these early galaxies presented. Normal galaxy growth follows a fairly predictable timeline. Small clumps of gas collapse under gravity, slowly forming stars, which then group together into larger structures over enormous stretches of time. Billions of years typically pass before a galaxy reaches the size and brightness these ancient objects already showed, at a point in cosmic history when the universe itself was still practically a newborn. Yet there they were, sitting in the data, fully formed and glowing brightly, far earlier than any existing model predicted they should. Scientists have a name for the general puzzle these objects represent, sometimes calling them galaxies that broke the timeline, because their existence challenges the standard picture of how galaxies are supposed to grow up slowly over cosmic time. This discovery connects directly back to everything explored so far. Just like the Big Ring appeared too large and too organized for its place in cosmic history, these early galaxies appeared too developed and too bright for theirs. Two completely separate puzzles, both pointing toward the same uncomfortable possibility that something about the early universe grew faster or differently than current models expect it to. Scientists have proposed a few different explanations, none of them fully confirmed yet. Perhaps early star formation happened in unusually efficient bursts, packing more growth into less time than typically expected. Perhaps measurement techniques themselves need refining, since measuring the true age and mass of an object billions of light years away is never a simple task. Both possibilities remain open, actively debated inside the astronomy community rather than settled with a clean answer. What stays confirmed is the observation itself. These galaxies exist. Their brightness and size have been measured carefully, checked against multiple methods, and confirmed by more than one research group working independently. The explanation for why they look this way remains the genuine mystery, an open question sitting at the center of modern astronomy right now. That mystery does not sit isolated from everything else in this story either. It joins a growing list of early universe objects, behaving in ways nobody fully predicted, each one adding pressure to the same underlying question about how quickly the young universe was truly capable of building things. That mystery does not stay isolated for long either, because the same detailed map that revealed these overgrown early galaxies also revealed something happening on the opposite end of a galaxy's life, an ending just as strange as this unexpected beginning. Every living thing eventually reaches an ending, and galaxies are no exception, even though their lifespans stretch across billions of years instead of decades. The new cosmic Webb map revealed something unexpected about exactly where that ending tends to happen most often, and the answer connects directly back to the structure of the Webb itself. Astronomers use a specific word for galaxies that have stopped forming new stars completely. They call these galaxies quiescent, meaning quiet, essentially retired from the business of building anything new. A galaxy like this still exists, still holds its stars and its shape, but it has stopped growing in the way younger, more active galaxies continue to grow. Here is the surprising pattern the map revealed. These quiet, retired galaxies do not scatter randomly throughout the universe. They cluster heavily inside the densest regions of the cosmic web, the crowded intersections where filaments meet and galaxies pack tightly together. Picture a crowded subway platform during rush hour, packed shoulder to shoulder, compared to an empty platform late at night with plenty of open space. Galaxies sitting in those crowded cosmic intersections seem far more likely to shut down and stop growing than galaxies sitting out in the emptier, quieter stretches of the web. Scientists have a working theory for why crowding might cause this shutdown, though it remains an active area of research rather than a fully settled fact. One leading idea points to size itself. Once a galaxy's surrounding halo of matter grows past a certain enormous mass, roughly equal to 1 trillion times the mass of our Sun, that halo may begin heating the surrounding gas so intensely that the gas can no longer cool down enough to collapse and form new stars. Growth ends up choking itself out simply by getting too big and too energetic. This connects the two puzzles from earlier chapters into a single, bigger picture. The universe is actively growing structures too fast and too large in places. It is also actively shutting down growth inside its most crowded neighborhoods, creating a strange mix of overachieving young galaxies in one part of the story, and burned out, retired galaxies clustered together in another. None of this happens evenly or randomly across the sky. It follows the shape of the cosmic web itself, meaning the invisible architecture connecting galaxies across the universe actively steers how they behave. It is steering how galaxies live, grow, and eventually stop growing altogether, based entirely on where they happen to sit within that structure. Think about how a plant grows differently depending on where it sits in a garden, thriving in open soil with plenty of light, struggling in a shaded, crowded corner where roots compete for the same limited resources. Galaxies appear to follow a similar rule, shaped less by anything unique about themselves and more by the crowded or empty neighborhoods surrounding them. And the thing responsible for shutting down some of these galaxies turns out to be even stranger than crowding alone, because hiding inside many of these dense regions sits something far more violent than simple overcrowding. Crowding alone does not tell the whole story of why galaxies stop growing. Hiding inside many of these dense, quiet regions of the cosmic web sits something far more violent, something capable of shutting down star formation across an entire galaxy almost on its own. Supermassive black holes, sitting at the centers of galaxies, turn out to play a major role in this story. Nearly every large galaxy holds one of these black holes at its core, an object so dense that nothing, not even light, can escape once it crosses a certain boundary. Most of the time, these black holes sit quietly, doing little beyond anchoring their galaxy's rotation. Sometimes, though, they become active, pulling in surrounding gas and dust, heating that material to extreme temperatures and blasting jets of energy outward at speeds approaching half the speed of light. Picture a fire hose blasting water at a flower bed, except instead of water, this hose blasts scorching hot particles outward at nearly the fastest speed anything in the universe is allowed to travel. Any gas caught in the path of a jet like that gets superheated instantly, stripped of the cool, calm conditions new stars actually need to form. A galaxy caught in the middle of this process effectively gets its star-forming fuel cooked away before it can ever be used. This process gives scientists another confirmed piece of the puzzle, explaining why so many galaxies inside dense regions of the cosmic web end up quiet and retired. Crowding alone does not explain it. Active, violent energy pours out from the very center of some galaxies, shutting down their own ability to keep growing from the inside out. Researchers found that this particular shutdown method, driven by these energetic black holes, dominated for roughly the first half of the universe's entire history. Only in more recent cosmic time did a different shutdown method take over, one driven more by a galaxy's surrounding environment, stripping away gas, rather than an internal blast from its own black hole. Two different eras, two different killers, both leaving their mark on the same structure. Think about how strange it is that the same object capable of trapping light forever is also capable of ending a galaxy's ability to grow, using nothing but raw energy blasted outward from its core. That is not a slow, quiet ending. That is closer to a controlled demolition happening in slow motion across millions of years. Researchers studying this process point out that not every black hole becomes active this way, and not every galaxy caught near an active black hole shuts down completely. The effect depends heavily on the exact conditions surrounding each galaxy, adding yet another layer of complexity to a picture that already resists simple, tidy explanations. With growth and death both mapped in detail now, one question remains hanging over everything explored so far. If galaxies keep shutting down across the universe, what does that mean for where all of this is eventually headed? Every story building toward this point has been leading somewhere, and the destination is not comforting. If galaxies across the universe are increasingly shutting down, growing quiet, and stopping their production of new stars, that pattern points towards something bigger than any single galaxy's fate. It points toward the long-term future of the entire universe itself. Star formation across the universe reached its peak billions of years ago, back when gas was still plentiful and conditions were still ideal for building new stars at a rapid pace. Since that peak, the overall rate of new star formation has been steadily declining, and the new cosmic web map only adds more detail to that already confirmed trend. More and more galaxies, especially the massive ones sitting inside crowded regions of the web, are slipping into that quiet, retired state as time moves forward. Picture a campfire slowly burning down after the wood stops getting added. The flames do not vanish instantly. They shrink gradually, glowing dimmer and dimmer until eventually only embers remain. The universe appears to be following a similar arc, just stretched across a timescale so enormous that no single human lifetime, or even human civilization, could ever witness the whole process unfold from start to finish. This does not mean stars are disappearing anytime soon, and it definitely does not mean anything dramatic is coming for Earth specifically. Stars that already exist will keep shining for billions more years, some of them far longer than that. What is changing is the overall rate of new stars being born across the universe. A slow, steady decline, rather than a sudden shutdown anyone needs to worry about personally. Here is why this connects back to everything covered already. The Big Ring showed structures growing strangely large and strangely fast, breaking the expected rules of cosmic growth in one direction. This new cosmic web map shows the opposite trend happening elsewhere, growth slowing down and quietly shutting off across huge stretches of the universe. Both patterns, growth breaking records in one place and shutting down in another, come from the same detailed map, the same careful survey, the same telescope staring patiently into the dark. Confirmed, cautious astronomers are quick to point out that this slow decline is not the same as a countdown to disaster. It is simply the natural next chapter in a universe that has already lived through billions of years of dramatic change, and will likely live through billions more before anything resembling an ending truly arrives. Human timescales make this easy to misread as urgent when it is not. A trend measured in billions of years moves so slowly that even tracking it requires comparing snapshots separated by enormous stretches of cosmic time, not the kind of change anyone could notice happening day to day, or even across an entire human lifetime. Still, standing at the edge of that slow decline raises a bigger question, one this entire journey has been circling from the very beginning. If the universe is not smooth, not predictable, and not even entirely finished revealing its secrets, what else is still waiting quietly in the dark for someone patient enough to notice it? Every mystery covered so far came from staring outward, far past our own galaxy, into the deep distance. This next one hides much closer, tucked directly behind the Milky Way itself, blocked from view for decades by our own cosmic backyard. Astronomers call this blind spot the zone of avoidance, a wide stretch of sky where the thick, dusty disk of our own galaxy blocks the view of everything sitting behind it. Picture trying to see through a thick curtain of fog rolled directly in front of your bedroom window. No matter how good your eyesight is, the fog blocks the view completely, hiding an entire street behind it. That is essentially what the plane of the Milky Way does to nearly 1/5 of the entire sky, hiding whatever sits behind that dusty curtain from ordinary telescopes for generations. For years, scientists suspected something large was hiding back there, based purely on strange, subtle tugs pulling at nearby galaxies, gravitational nudges with no visible source. Something massive was clearly influencing its surroundings. Nobody could see what it was. Using special techniques designed specifically to peer through galactic dust, astronomers finally mapped what had been hiding there all along. The answer turned out to be enormous. A supercluster of galaxies, sitting roughly 800 million light-years away, stretching across a distance about 3,000 times wider than our entire Milky Way. Confirmed measurements placed its total mass at roughly 30 quadrillion times the mass of our Sun, an amount almost too large to hold in your head properly. Picture every grain of sand on every beach on Earth, then imagine that number still falling short of describing the scale involved here. Even stranger, the map revealed that most of this mass sits concentrated into two separate cores, both moving steadily toward each other, locked in a slow gravitational dance that will likely end in a massive collision somewhere far in the future. Researchers described this discovery as a coherent, real structure comparable in scale to some of the largest superclusters already known and confirmed anywhere in the local universe. This connects directly back to everything explored already. The universe keeps hiding enormous structures in the last places anyone thought to look, whether wrapped behind a billion-year-old ring near Boötis, or sitting quietly behind the dusty curtain of our own galaxy this entire time. Confirmed and measured, this supercluster proves the universe still has enormous surprises tucked into blind spots nobody has fully explored yet. Think about how long it took to even suspect something was there. Astronomers noticed the gravitational tugging decades before they had the tools to actually confirm the source. That gap between suspicion and proof shows just how patient this kind of science has to be, waiting years, sometimes decades, for technology to finally catch up to a hunch. And blind spots like this one raise an uncomfortable question. If something this massive could hide directly behind our own galaxy for this long, what else might still be sitting undiscovered, waiting patiently in a blind spot nobody has thought to check yet? Every object discussed so far has been visible in some way, whether through direct light or through its gravitational influence on its surroundings. This next discovery breaks that pattern entirely. Scientists using the James Webb Space Telescope detected a black hole so well hidden it does not show up in any wavelength of light at all, not one single type of light across the entire spectrum. Normally, black holes reveal themselves indirectly. As matter falls toward one, it heats up violently and glows brightly before disappearing past the boundary of no return. giving off light that telescopes can detect even from billions of light years away. That glow is usually the giveaway. The fingerprint proving a black hole is there, even though the black hole itself stays invisible. This particular black hole skipped that step entirely. Sitting roughly 10 billion light years away, it showed no glow, no telltale signature, nothing detectable across any wavelength scientists checked. Picture searching a dark room for a friend using a flashlight and finding every single spot on the wall lit up, except for one perfectly black outline where your friend happens to be standing, betrayed only by the shape of the missing light around them. That is essentially how scientists found this black hole, not by seeing it directly, but by measuring its gravitational effect on the galaxy surrounding it, calculating a mass roughly 6 billion times heavier than our Sun, based entirely on how strongly it pulled on nearby stars and gas. A gap in the data, shaped exactly like a monster hiding inside it. Scientists have given objects like this a fitting nickname, calling them sleeping giants, because they sit dormant, inactive, not currently feeding on surrounding material the way more famous, glowing black holes do. Confirmed as one of the most distant dormant black holes ever measured, this discovery proves that plenty of the universe's largest objects are not announcing themselves with dramatic light shows at all. Many of them sit quietly in the dark, detectable only through the subtle fingerprints they leave behind on everything nearby. That raises an uncomfortable thought worth sitting with. If a black hole 6 billion times heavier than our Sun can hide completely invisible across every wavelength of light, then plenty of similarly massive objects could be scattered throughout the universe right now, completely undetected, simply because nobody has found the right gravitational fingerprint yet. Finding an object like this required an enormous amount of patience and careful cross-checking. Researchers had to rule out every ordinary explanation for the gravitational pull first, confirming step by step that no visible source could account for it, before finally accepting that the missing piece really was a black hole in hiding. This sleeping giant was strange enough on its own. But the next black hole discovery breaks an even more basic rule, one involving the order objects are supposed to form in. Some discoveries break the rules of size, others break the rules of timing. This next one breaks the rules of order itself. The basic sequence scientists assumed had to happen first, second, and third when it comes to how galaxies and their black holes come into existence. Normal galaxy formation follows an assumed order. A galaxy begins forming first, gas and stars slowly collecting together under gravity. Only afterward, once enough material has gathered near the center, does a supermassive black hole typically form and grow, feeding on the surrounding material that the galaxy provided in the first place. Galaxy first, black hole second. That has been the expected sequence for decades. Scientists using the James Webb Space Telescope found an object that flips that entire sequence on its head, nicknamed a naked black hole. This object appears to have formed before its own galaxy existed around it, sitting essentially alone, without the surrounding structure a black hole is supposed to need in order to grow in the first place. Picture building the foundation of a house, except somehow the completed roof shows up first, floating in place, with no walls or foundation built underneath it yet. That backwards construction order is exactly the kind of problem this black hole presents. It should not have been possible to grow this massive without a galaxy already in place to feed it. Yet there it sits, confirmed and measured, existing seemingly ahead of schedule. This discovery connects directly to a larger pattern building across this entire journey. Structures growing too large too early, galaxies looking too developed too soon. Now a black hole apparently skipping a required step in its own formation entirely. Each mystery on its own might be dismissed as an unusual exception. Stacked together, they start looking like evidence that the early universe operated under rules scientists have not fully figured out yet. Researchers have proposed a theory to explain this backwards order, involving massive clouds of gas collapsing directly into a black hole without ever forming stars first, skipping several expected steps entirely. This remains a theory, an idea still being tested against the data rather than a confirmed explanation everyone agrees on. Confirming this order really was reversed took careful, repeated measurement, checking the surrounding region for any sign of an early galaxy that might have simply been too faint to notice at first. Even after that careful search, the region around this black hole stayed unusually empty, reinforcing the strange possibility that it truly did arrive first. Whatever the explanation turns out to be, one thing stays clear. The early universe keeps breaking the assumed order of operations, growing things too big, too fast, and now apparently in the wrong sequence entirely. And the deeper researchers dig into this pattern, the stranger the next class of object they found becomes. Buried inside the flood of new data from deep space surveys, scientists kept noticing tiny, unusually red points of light scattered throughout the earliest images of the universe. Small, faint, easy to overlook at first glance. Astronomers eventually gave them a simple, almost casual nickname, calling them little red dots, even though what they might actually represent turned out to be anything but simple. At first, researchers assumed these dots were just compact, extremely early galaxies, small clusters of stars glowing faintly from an enormous distance. The deeper scientists studied them, though, the stranger their properties looked. Many appeared far too bright and far too red for their apparent size, behaving less like an ordinary young galaxy and more like something entirely different hiding inside a galaxy-shaped disguise. Picture spotting a firefly blinking in a dark backyard, except when you finally get close enough to look carefully, it turns out to be glowing far too brightly and far too steadily to actually be a firefly at all. That mismatch between what something looks like from a distance and what it turns out to be up close captures exactly the puzzle these little red dots present to researchers. One leading theory, still very much a theory rather than a settled fact, suggests these dots might represent an entirely new type of object, perhaps the earliest generation of stars ever formed in the universe, now caught in the final stages of collapsing inward on themselves. Under this idea, what looks like a small galaxy might actually be a single, enormous, dying star from the very first generation the universe ever produced, glowing with a strange, reddish light as it collapses. Another competing theory points toward black holes instead, suggesting these dots might be small, actively feeding black holes wrapped in thick clouds of dust and gas, disguising their true nature and making them mimic the appearance of a compact galaxy from a distance. Both explanations remain actively debated, with researchers still gathering more detailed observations to figure out which theory, if either, holds up under closer inspection. What stays confirmed through all of this uncertainty is the simple fact that these objects exist in large numbers, showing up repeatedly across multiple deep field surveys, refusing to fit neatly into any previously known category of object. That alone marks a genuine discovery, an entirely new mystery uncovered simply by looking closely enough at the earliest, faintest corners of the observable universe. The sheer number of these dots makes them hard to treat as some rare fluke buried in the data. Survey after survey keeps turning up more of them, scattered across different patches of sky, suggesting whatever they are, they represent a common feature of the early universe, rather than a one-time oddity nobody will ever see again. Whatever these little red dots eventually turn out to be, they represent something the universe has apparently been hiding in plain sight this entire time, tucked inside data that older, less sensitive telescopes were simply never sharp enough to properly resolve. Sometimes the strangest discoveries come from watching two objects collide and produce something nobody expected to find in the wreckage. That is exactly what happened when researchers studying Webb data found a system nicknamed the Infinity Galaxy, and inside it, a black hole that appears to be forming in a way current models struggle to explain. The system earned its nickname from its shape. Two massive, ringed structures sit connected together, forming something that resembles the infinity symbol stretched across the sky, the kind of shape usually drawn with one continuous, looping line. That shape alone made the system stand out immediately in the survey data, unusual enough to draw a closer look from researchers scanning through thousands of images. What made this discovery genuinely remarkable sits directly between those two ringed structures. Scientists identified strong evidence for a supermassive black hole candidate forming in the space connecting the two colliding galaxies, rather than sitting safely at the center of either one individually. Picture two cars colliding head-on, and instead of the wreckage scattering outward the way you would expect, something entirely new and unexpected assembles itself directly in the space between the two vehicles. This matters because it may represent direct evidence for an idea scientists have discussed only in theory for years, called direct collapse. Under normal circumstances, a black hole grows slowly, starting small and gradually feeding on surrounding material over enormous stretches of time. Direct collapse describes a shortcut, a scenario where a massive cloud of gas collapses straight into a black hole without ever passing through the slower, normal growth stages first. If confirmed through further study, this system would help explain a puzzle raised earlier in this journey, the mystery of black holes appearing too early and too massive for the standard slow growth timeline to account for properly. A direct collapse process occurring during a galaxy collision could explain how some black holes manage to skip years, even eras, of expected gradual growth. This remains an active area of research, with the black hole candidate still being studied and confirmed through additional observations rather than treated as a fully settled discovery. Still, finding a system like this, caught in the exact act of potentially building a black hole through an entirely different process than usual, offers a rare, direct window into a process scientists have only theorized about until now. Researchers plan to keep watching this exact system closely over the coming years, hoping to catch further changes as the collision continues to unfold. Catching a process like this in progress, rather than only seeing the finished result afterward, gives scientists a rare chance to test their theories against something actually happening in real time. Combined with the naked black hole and the sleeping giant covered earlier, this discovery adds another piece to a growing puzzle. The early universe appears to have multiple pathways for building these massive objects, some of them stranger and faster than anyone predicted before Webb started looking closely enough to catch them in the act. Step back for a moment and lay every discovery from this journey side by side. A ring far too large to exist, galaxies far too developed for their age, black holes forming before their own galaxies, hiding invisible across every wavelength, or assembling directly between two colliding systems entirely. Individually, each discovery sounds like an isolated oddity. Placed together, a single pattern emerges clearly, and it is impossible to ignore once you see it. That pattern has a simple name, even if the explanation behind it remains genuinely complicated. Too early, too fast. Structure after structure, across completely different categories of object, keeps showing up ahead of schedule, more developed than the standard timeline of the universe says should be possible at that particular point in cosmic history. Picture reading a mystery novel where every single chapter reveals a character who somehow already knows the ending before the story has even properly begun. One character like that might just be a clever writing choice. An entire cast of characters behaving that way suggests something bigger is going on beneath the surface of the story, something the reader has not been told yet. Scientists studying the early universe are facing something similar right now. The Big Ring formed too fast for its size. Certain galaxies grew too bright and too large for their age. Black holes assembled ahead of the galaxies meant to host them. Even the little red dots, whatever they eventually turn out to be, showed up in numbers nobody expected to find this early in cosmic history. Different objects, different discoveries. The exact same underlying problem, repeating itself again and again across the data. This does not automatically mean the standard model of the universe is wrong. Confirmed observations like these usually lead to refinement rather than complete replacement, adding new details and exceptions to an existing picture rather than tearing the whole picture down and starting over from scratch. Still, a pattern this consistent, showing up across so many completely different types of objects, is difficult for scientists to wave away as simple coincidence or measurement error. Researchers are now actively working to figure out whether a single, unified explanation might connect all of these separate mysteries together. Some shared ingredient in the early universe that made faster, bigger, earlier growth possible across the board, or whether each mystery has its own separate explanation, and the timing similarities are simply an eerie coincidence born from studying the same early era of cosmic history over and over. Either way, the pattern itself stays confirmed and impossible to dismiss. Something about the early universe behaved differently than current models expect, and untangling exactly why has become one of the biggest open questions in modern astronomy today. Standing at this point in the journey, it helps to remember how each individual piece was found, not through guesswork or wild speculation, but through careful, repeated measurement, cross-checked by multiple teams, published for anyone in the field to challenge and verify. That is exactly why this pattern carries real weight instead of getting dismissed as an internet rumor. Scientists tend to speak carefully, choosing words that undersell rather than oversell a discovery. That habit makes it worth paying close attention whenever a researcher breaks from that pattern and reaches for stronger language instead. When the team behind the new cosmic Webb map described their own results, one of the lead researchers called the achievement truly significant, a phrase that carries real weight coming from someone trained to avoid exaggeration. That researcher pointed specifically to how much deeper this survey could see compared to anything that came before it, reaching back to a time when the universe was only a few 100 million years old, an era essentially out of reach for any earlier telescope. Picture trying to read a message written in pencil, faded almost completely after years in the sun, and suddenly getting handed a version rewritten in bold, dark ink. That jump in clarity is roughly what shifting from older telescopes to this new survey represents for scientists studying the deep universe. Words like these matter because they come from someone who spent years working directly with the data, not from a headline writer looking for something dramatic to print. When a professional physicist uses the word significant without qualifying it, without softening it, that choice reflects genuine confidence in what the data actually shows, confirmed through careful analysis rather than excitement or guesswork. This distinction matters throughout this entire journey. Confirmed discoveries, like the size and existence of the Big Ring, or the detailed structure of the cosmic web itself, rest on solid, repeatable measurement. Theories, like cosmic strings or bubble universe collisions, remain honest possibilities, still waiting for stronger evidence. Keeping that line clear protects real science from getting lumped in with wild speculation, even when both sound equally strange to someone hearing about them for the first time. The significance being described here reaches beyond just one impressive map. It represents a genuine shift in what scientists are capable of observing directly, opening up an era of the universe that used to exist only as rough, theoretical guesswork. Turning guesswork into confirmed measurement is exactly the kind of progress that pushes an entire field of science forward. Standing at this point, the honest question becomes what happens next. A tool capable of producing results serious enough to earn the word significant from a careful scientist is a tool capable of finding even more surprises hiding in the data, still waiting to be analyzed. Think about how rare it is for someone deep inside a field to sound genuinely amazed by their own results. Most days, research moves in small, careful steps, rarely producing a moment big enough to justify strong language. When that moment does arrive, it tends to mark something researchers will keep referencing for years afterward, a turning point, rather than just another data point added to a growing pile. And plenty of that data is still sitting there, waiting for the right question to unlock what it is quietly holding. Every scientific model eventually reaches a moment where enough small cracks add up to something bigger, a point where careful researchers start asking whether the model itself needs revision rather than just another small patch. Cosmology may be approaching exactly that kind of moment right now, based on everything explored across this entire journey so far. The standard model of the universe rests on a handful of core assumptions, including the idea that matter spreads out smoothly and evenly once you zoom out far enough. That assumption has worked remarkably well for decades, successfully predicting all sorts of observations about how the universe looks and behaves. A model does not earn decades of trust by being wrong most of the time. Still, models earn revisions the same way trust gets rebuilt after repeated surprises. One oversized structure might be dismissed as a rare statistical fluke, unlikely but not impossible under the existing rules. A second oversized structure, sitting nearly in the same patch of sky, makes that explanation harder to accept. Add galaxies growing too fast, black holes forming out of order, and an entire cosmic web map revealing far more structure and complexity than expected, and the case for a fluke starts collapsing under its own weight. Picture a building inspector finding one small crack in a wall and shrugging it off as normal settling. Finding 10 more cracks across different rooms changes the conversation entirely, shifting from casual dismissal toward genuine concern about the building's foundation itself. Cosmology is not at the point of declaring the foundation broken. It is absolutely at the point where careful inspectors are taking a much closer look than before. This does not mean the Big Bang theory itself is wrong, and it definitely does not mean everything scientists currently understand about the universe collapses overnight into chaos. It means specific assumptions built into the model, particularly around how smoothly matter is expected to spread out at the largest scales, are facing genuine, serious scrutiny for the first time in years. Scientists disagree, sometimes strongly, about how serious this scrutiny should be. Some researchers view these discoveries as expected statistical outliers that will smooth out once more data comes in. Others view them as early signs of a bigger revision on the horizon. Both camps are actively publishing research, actively debating the evidence, and actively pushing the field forward through healthy scientific disagreement rather than quiet dismissal. That disagreement itself is a healthy sign, not a warning sign. Science moves forward exactly through moments like this, when confirmed observations start pressing hard enough against existing assumptions that careful people are forced to ask difficult, uncomfortable questions out loud. History offers plenty of examples of models bending under exactly this kind of pressure, only to come out stronger and more accurate afterward. Every major shift in how scientists understand the universe started with small, stubborn anomalies that refused to disappear no matter how many times researchers double-checked their work. The anomalies piling up right now may follow that same familiar path. Suppose, for a moment, that enough evidence eventually builds up to force a real revision in how scientists model the smoothness of the universe. What would actually change, in practical terms, if that moment arrives someday? The answer touches almost everything cosmologists use to describe the history and future of the cosmos. Distance calculations across the universe rely heavily on assumptions about smooth, even expansion. If matter turns out to be clumped more dramatically than expected in certain regions, some of those distance calculations could shift slightly, affecting how precisely scientists measure the size and age of the observable universe itself. Not a small correction buried in a footnote. A meaningful recalibration touching calculations used across the entire field. Picture adjusting a recipe that has been used successfully for years, only to discover one ingredient needs a slightly different amount than originally measured. The dish does not turn out completely different. It turns out better, more accurate, closer to what was actually intended all along. That is roughly the kind of adjustment scientists are discussing here. Refinement rather than a total rewrite from scratch. The age of the universe itself, currently estimated at around 13.8 billion years, rests on calculations that assume a certain rate and pattern of expansion. Structures, like the Big Ring, existing earlier and larger than expected, could nudge those calculations in small but meaningful ways, depending on exactly how common structures like it turn out to be once more surveys are completed. Here is why this matters beyond academic curiosity locked inside research papers. Every prediction about the universe's ultimate future, whether it keeps expanding forever, slows down eventually, or something else entirely, depends on getting these underlying assumptions right in the first place. A meaningful correction to how matter is distributed could shift those long-term predictions in ways scientists are only beginning to explore carefully. None of this suggests panic is appropriate, and careful researchers are quick to stress exactly that point whenever this topic comes up. Science has weathered major revisions before, emerging stronger and more accurate each time, rather than collapsing under the weight of new evidence. Revisions represent progress, not failure, even when they force uncomfortable conversations about ideas that felt solid for a very long time. What stays true either way is this: the universe recently proved it, still has surprises capable of nudging even its most trusted, decades-old assumptions. That alone marks a genuinely remarkable moment in the ongoing story of how humans slowly piece together the true shape of everything around them. Consider how strange it is that a shape found accidentally in a graduate student's data could eventually ripple outward into calculations, touching the entire scale and age of everything that exists. That is the quiet power hiding inside careful, patient science, where one small, honest observation can eventually reshape ideas that felt permanently settled for generations. Discoveries this strange invite an obvious, reasonable question: is any of this actually taken seriously by real scientists? Or does it belong more to speculative blogs and wild internet theories than to careful, peer-reviewed research? The honest answer matters, and it points firmly toward legitimate, mainstream science rather than fringe speculation. Every major claim explored across this journey traces back to published research, appearing in respected, peer-reviewed journals where other experts in the field carefully check the work before it ever gets published publicly. The Big Ring's discovery, the detailed cosmic web map, the naked black hole, the sleeping giant, each one went through this same rigorous process, involving researchers at established universities using publicly documented methods anyone can review and challenge. Picture the difference between a rumor spreading through a school hallway and a fact-checked story running in a trusted newspaper, with named sources, reviewed evidence, and editors checking every detail before publication. Peer review works similarly for scientific discoveries, adding a careful layer of scrutiny specifically designed to catch mistakes before claims ever reach the public eye. The researchers behind these discoveries work at recognized institutions, including major universities with long histories of respected astronomical research. Their findings get presented at scientific conferences, discussed openly among colleagues, and tested repeatedly by other independent teams trying to either confirm or challenge the original results. That process of open challenge is exactly what separates real science from unchecked speculation floating around without any accountability. This matters enormously for how seriously these discoveries deserve to be taken. A wild claim posted anonymously online carries no accountability behind it. A claim published in a respected astrophysics journal, backed by named researchers willing to defend their methods publicly, carries an entirely different kind of weight and credibility. None of this means every theory discussed throughout this journey is proven fact. Cosmic strings remain unconfirmed. Bubble universe collisions remain speculative. That distinction has been kept clear intentionally throughout every chapter covered so far. What stays true regardless is that the questions being asked and the observations driving those questions come from legitimate, careful, professional science, not fringe speculation dressed up to look convincing. Understanding that distinction changes how seriously this entire story deserves to be taken. This is the genuine, ongoing frontier of modern astronomy, playing out in real time, with real consequences for how humans understand their place in the universe. It also means anyone curious enough can follow along as it unfolds. Papers describing these discoveries get posted publicly before formal publication, letting anyone willing to dig through the details watch the scientific process happen in something close to real time, rather than waiting years for a tidy summary to arrive. It helps to remember that skepticism is actually built directly into how this entire process works. Researchers publishing these results expect other scientists to try tearing their conclusions apart, searching for flaws, testing alternative explanations, and demanding stronger evidence before accepting anything as settled. Surviving that gauntlet repeatedly is exactly what gives these discoveries their credibility today. Long journeys benefit from occasionally stopping to look back at exactly how far they have traveled. Laid out side by side, every mystery explored across this journey starts forming a picture bigger than any single discovery could reveal on its own. It began with a ring, 1.33 billion light years wide, sitting in a spot in the sky where it should not have had time to form. Nearby, an arc almost as strange, discovered by the same researcher, raising the possibility that both structures might connect into something even larger, still waiting to be fully mapped. Together, both structures challenge one of cosmology's oldest, most trusted assumptions: the idea that the universe should look smooth, and even once you zoom out far enough. From there, the journey widened dramatically. An enormous survey mapped the cosmic web itself in unprecedented detail, revealing galaxies that grew too fast, too early, alongside other galaxies clustering together and quietly shutting down inside the web's most crowded intersections. Supermassive black holes turned out to be responsible for some of that shutdown, blasting scorching jets of energy outward and choking off the fuel needed for new stars to form. Then came the discoveries that broke expected order entirely. A black hole hiding completely invisible across every wavelength of light. Another black hole appearing to form before its own galaxy existed around it. A colliding pair of galaxies potentially caught in the act of building a black hole through an entirely new process scientists had only theorized about previously. And scattered throughout the earliest images available, mysterious little red dots refusing to fit into any category anyone had prepared in advance for them. Even our own cosmic backyard turned out to hide secrets. An enormous supercluster, sitting directly behind our own galaxy, hidden for years simply because our own galactic dust blocked the view completely, waiting patiently for the right tools to finally reveal it. Picture standing back from a jigsaw puzzle after placing several dozen unconnected pieces down at once. No single piece explains the full picture on its own. Placed together, though, a pattern starts emerging, hinting at a bigger image than anyone expected walking into this project. That is roughly where cosmology finds itself standing right now, surrounded by confirmed, individually strange pieces, slowly working toward understanding how they might all connect. Nobody has assembled the complete picture yet, and that honesty matters more than pretending otherwise. What stays certain is this: each piece, examined carefully and independently, keeps pointing toward the same underlying truth. The universe still holds far more surprises than anyone assumed possible, hiding in plain sight, waiting for sharper eyes and more patient scientists to finally notice them. Notice, too, how many of these pieces trace back to a single upgrade in observing power, one sharper telescope catching light that older instruments simply could not reach. That alone suggests the picture is still far from finished, since every improvement in observing power throughout history has revealed a universe stranger and more detailed than the one that came before it. Every discovery covered so far has stayed billions of light years away, safely distant from anything touching daily life on Earth directly. It is worth asking honestly what any of this actually means closer to home, if it means anything practical at all, beyond simple curiosity about the universe. The direct answer is refreshingly simple. None of these discoveries change anything about tomorrow morning here on Earth. The sun will rise the same way it always has. Gravity will keep working exactly the same way it always has. Nothing about a ring 1.33 billion light years away reaches out and touches daily life in any measurable, practical sense. What actually changes is something quieter, harder to measure, but still genuinely significant in its own way. Humanity's sense of its own place inside the universe shifts slightly every time a discovery like this arrives. Picture believing your neighborhood was the entire world, only to slowly discover an entire ocean, an entire continent, and eventually an entire planet, stretching out far beyond what you originally imagined. Each new discovery does not change your actual neighborhood. It changes your understanding of how small that neighborhood truly is compared to everything surrounding it. That shift matters beyond simple philosophy. The same careful thinking, the same patient measurement, and the same willingness to question comfortable assumptions that led to discoveries like the Big Ring also drive advances much closer to home, from medical imaging technology to the satellites providing weather forecasts and navigation systems people rely on every single day. Curiosity aimed at distant galaxies frequently produces tools and techniques that end up solving problems much closer to Earth. There is also something valuable in simply sitting with genuine mystery instead of rushing toward false certainty. The universe just proved, through multiple independent, confirmed discoveries, that it still holds far more surprises than anyone assumed possible only a few years ago. That kind of humility, admitting honestly what remains unknown rather than pretending otherwise, tends to produce better thinking far beyond astronomy alone. None of this makes the discoveries feel less important simply because they stay physically distant from daily life. If anything, it makes them feel more valuable. Proof that curiosity aimed purely at understanding, without any immediate practical payoff required, can still reshape how an entire species understands its own place inside something far larger than itself. Think about how many everyday tools trace their roots back to someone studying something that seemed completely disconnected from daily life at the time. Nobody chasing black holes or ancient galaxies sets out planning to improve a hospital scanner or a phone's camera sensor. Those improvements arrive as side effects of building better instruments, more sensitive detectors, and smarter ways of processing enormous amounts of data, all originally designed to answer questions about the deep sky. Standing at the edge of everything explored so far, one more question remains before this particular journey reaches its end. What comes next for the scientists chasing these mysteries even further? Every mystery explored throughout this journey shares one thing in common. None of them arrived as a finished, fully explained story. Each one represents an open door, a question actively driving new research, new observing time, and new surveys currently being planned or already underway across the astronomy community. Telescopes capable of catching the kind of detail needed to properly study these mysteries remain extremely limited and heavily requested. Researchers compete fiercely for observing time on instruments like the James Webb Space Telescope, submitting detailed proposals, explaining exactly why their particular mystery deserves a share of the telescope's extremely limited schedule. Time pointed at one target is time not available for another, forcing difficult choices about which questions get answered first. Picture an enormous line of people waiting outside a single door, each one holding an important, urgent question, knowing only a small handful will get invited inside before the day ends. That is roughly what competing for observing time on a major telescope actually feels like from inside the research community. A constant balancing act between countless worthy, competing priorities. Despite that competition, plans are already moving forward, specifically targeting several mysteries covered throughout this journey. Additional surveys aim to search for more ring-shaped or arc-shaped structures scattered throughout the sky, testing whether Botas truly is unique or whether similar formations are hiding elsewhere, simply waiting to be found with the right tools pointed in the right direction. Other planned observations aim to study little red dots in far greater detail, hoping to finally settle the debate over what they actually represent. Meanwhile, upcoming space telescopes, still years away from launching, promise even sharper vision than anything currently available, potentially capable of resolving details that remain frustratingly blurry using today's best instruments. Each generation of telescope tends to answer some existing questions, while immediately raising several brand new ones nobody had thought to ask yet. This race for better data is not driven by simple curiosity alone. Confirmed anomalies, the kind explored throughout this entire journey, carry real scientific weight. Enough weight to justify dedicating enormous amounts of expensive, limited observing time toward chasing down proper answers. That level of institutional commitment signals just how seriously the broader scientific community is taking these mysteries. Whatever answers eventually arrive, they will almost certainly raise fresh questions immediately afterward, continuing a cycle that has driven astronomy forward for centuries. That cycle shows no sign of slowing down anytime soon, especially with tools this powerful only just beginning to reveal what they are truly capable of uncovering. Public data releases add another layer to this race, letting researchers outside the original teams dig through the same information, looking for patterns the first group might have missed entirely. Some of the most interesting follow-up findings in astronomy come not from the team that captured the data, but from someone else entirely, approaching the same numbers with a completely different question in mind. That openness turns every major survey into a gift that keeps producing results long after its official publication date. A student working from a laptop on the other side of the world can pull the exact same catalog used to find the Big Ring, or the exact same cosmic web map built from over 160,000 galaxies, and go hunting for something the original team never thought to check. Some of tomorrow's biggest headlines may already be sitting inside files published quietly months or years ago. Long journeys through strange, complicated territory eventually reach a point demanding honest reflection rather than more forward momentum. Having traveled from a single accidental ring discovery all the way through black holes, dying galaxies, hidden superclusters, and theories stretching toward other universes entirely, it helps to pause and take stock of exactly where the boundary between confirmed fact and open theory actually sits. Confirmed, solid ground includes the Big Ring's existence, its staggering size, and its location deep in the early universe. It includes the detailed cosmic web map, built from over 160,000 carefully measured galaxies. It includes specific black holes, found hiding invisible, or appearing to form before their own galaxies existed. It includes an enormous supercluster, hidden for years directly behind our own galaxy. All of this rests on published, peer-reviewed, independently checked research. Theory, meanwhile, includes cosmic strings, bubble universe collisions, and the deeper explanation behind exactly why so many early objects grew too large and too fast for the standard timeline to properly explain. These ideas remain genuinely serious, actively studied by respected researchers, yet still unconfirmed, still waiting for stronger evidence before earning a permanent place in textbooks. Picture standing at the edge of a well-lit room, staring out through an open doorway into a much darker hallway stretching beyond it. The lit room represents everything confirmed and solid. The dark hallway represents genuine mystery, real, but not yet fully understood. Good science means staying honest about exactly where that doorway sits, refusing to pretend the dark hallway is already fully lit just because that would feel more satisfying or more comfortable. That honesty is not a weakness in how science works. It is the entire point. Admitting what remains unknown protects against the kind of overconfident, sloppy thinking that leads researchers astray, chasing false certainty instead of patiently building toward real, durable understanding over time. Standing here, at the true edge of what is currently known, the appropriate feeling is not disappointment that answers remain incomplete. It is something closer to anticipation, genuine excitement for what comes next, once better tools and more patient observation finally push that doorway open just a little bit further than it currently sits. Because if this journey has proven anything clearly, it is that the darkness just beyond the edge of the known rarely stays empty for long once someone patient enough finally decides to go looking. Every scientist quoted throughout this journey, whether describing a ring, a dying galaxy, or a hidden supercluster, shared that same careful mix of confidence and humility. Confident enough to publish a genuinely strange result, humble enough to admit clearly where the explanation runs out and honest uncertainty begins. That balance is worth remembering long after the specific details of any single discovery fade from memory. That balance is also worth carrying into everyday life, far beyond astronomy specifically. Admitting what you do not yet know, while still trusting what careful evidence actually shows, tends to lead toward better decisions in everyday life, well beyond science published in a journal somewhere. Every mystery covered throughout this entire journey started the exact same way as an ordinary observation that quietly refused to behave the way anyone expected it to. A graduate student noticed an unusual curve in a pile of quasar data. A survey team noticed galaxies growing too fast for their age. A research group noticed a gravitational tug with no visible source hiding behind it. None of these discoveries required flashy equipment nobody had heard of. They required patience, careful measurement, and a genuine willingness to trust the data over comfortable assumptions. That pattern matters beyond just explaining how these specific discoveries happened. It suggests something optimistic about everything still sitting undiscovered throughout the rest of the universe. If a ring 1.3 billion light-years wide managed to hide successfully until a graduate student happened to notice it by accident, then plenty of other genuinely enormous, genuinely strange structures are almost certainly still sitting out there right now, simply waiting for the right person, pointing the right instrument in the right direction at the right moment. Picture standing on a beach at night, holding a single flashlight, aimed at one small patch of sand directly in front of your feet. Everything the light touches becomes visible and clear. Everything just outside that narrow beam stays completely hidden, simply because nobody has pointed the light in that particular direction yet, not because it is somehow missing from the sand. Astronomy right now resembles exactly that kind of beach, an entire universe of unexplored sand stretching out far beyond wherever the current beam of observation happens to be pointing. Every telescope built represents a slightly wider, slightly brighter beam, capable of illuminating more sand than the tools that came before it. Every wider beam has revealed genuine surprises, structures, and objects nobody predicted in advance, hiding patiently in territory nobody had properly illuminated until that exact moment arrived. There is no solid reason to believe that pattern is anywhere close to finished playing out. This is precisely why discoveries like the ones covered throughout this journey matter so much, beyond simple entertainment value alone. Each one proves, clearly and repeatedly, that confident assumptions about a smooth, fully understood, predictable universe remain premature. Genuine surprise is still entirely possible, hiding in ordinary-looking data, waiting patiently for someone curious enough to look closely and refuse to look away once something strange finally appears. The next major discovery might already be sitting quietly inside a dataset somewhere, uploaded, stored, and waiting patiently, simply because nobody has looked at it carefully enough yet to notice. Consider how young this entire era of discovery still is. Every structure and object covered throughout this journey emerged only within the past few years, made possible by instruments that barely existed a decade ago. If this much strangeness turned up this quickly, the coming years, backed by even sharper tools, seem almost certain to turn up plenty more. That thought alone is enough to make looking up at night feel different than it used to. The same dark sky that looked empty and quiet centuries ago turned out to be holding rings, hidden black holes, and entire superclusters this whole time, simply waiting for someone with the right instrument to finally notice. Every journey through strange territory eventually has to end somewhere, even when the mystery itself has no true finish line in sight. This one began with a single accidental discovery, a graduate student noticing a shape that refused to behave the way it was supposed to. It grew from there into an entire universe of open questions, stretching from black holes hiding in plain sight to structures so large they challenge some of cosmology's oldest, most trusted assumptions. What connects every single chapter of this journey is not really the specific objects themselves, strange and fascinating as each one turned out to be. It is the simple, quiet decision to keep looking closely, refusing to accept the first easy explanation, refusing to look away just because an answer felt uncomfortable or difficult to fully explain. That decision, repeated patiently over and over by researchers working through mountains of careful data, is exactly what turned scattered points of light into genuine, confirmed discoveries. Picture the night sky the way it looked centuries ago, before telescopes existed at all. Just scattered points of light overhead, with no way to know what any of them truly represented. Every single discovery covered throughout this journey exists only because someone, at some point, refused to accept that the sky had already revealed everything it had to offer. That refusal, stretched patiently across generations of curious scientists, is precisely how humanity slowly built its current understanding of the universe, one confirmed discovery at a time. The sky is not finished revealing itself, and nothing covered throughout this entire journey suggests it ever will be. Structures like the Big Ring, discoveries like the cosmic Webb map, mysteries like the little red dots, all of them arrived recently, within the last few years, proving conclusively that even familiar patches of sky still hold genuine surprises for anyone patient enough to look carefully. That is the quiet invitation sitting behind every single discovery explored throughout this journey. Not an invitation reserved only for professional astronomers working at major universities with access to billion-dollar telescopes. An invitation extended to anyone willing to look up, stay genuinely curious, and remember that even the most familiar-looking patch of sky might still be hiding something nobody has properly noticed yet. Somewhere out there tonight, in a dataset nobody has fully examined, or in a patch of sky nobody has pointed the right instrument toward yet, another impossible structure is almost certainly waiting patiently in the dark, waiting for someone curious enough to finally notice it and brave enough to trust exactly what the data reveals, no matter how strange that answer eventually turns out to be. That is where this particular story ends for now, though the sky itself is nowhere near finished telling it. Every discovery covered tonight started as a single moment of noticing, one person refusing to look away from something strange. The next chapter of this same story is still being written, quietly, somewhere in the dark, waiting for its own moment of discovery to finally arrive.